What if I told you that until observation or measurement occurs, we can't necessarily say a physical quantity has a definite value? What if, until measured, an electron exists in a superposition, both wave and particle, at once? In 1927, Heisenberg published the uncertainty principle. An electron's position and momentum cannot both be measured with perfect precision simultaneously. This isn't a limitation of measurement. The electron simply doesn't possess both position and momentum at the same time. Until observed, these values remain undefined. If this is true, what does it mean for the objective reality we've always believed in? In a universe without observers, what exists? Today, let's explore one of quantum mechanics' deepest mysteries, the measurement problem. By the time you finish this video, the very meaning of seeing will have fundamentally changed for you. Chapter 1. The Electron's Two Faces. Around 1801, Thomas Young published experiments and interpretations demonstrating light interference. A pattern of bright and dark bands appeared on the screen. This became the foundation for what would later be systematically organized as the double-slit experiment in textbooks. Waves interfere. Two waves overlap, reinforcing and canceling each other. That's why the pattern forms. In the 20th century, scientists performed the same experiment with electrons. Electrons are particles. They were thought to be like tiny spheres. But here's where reality becomes stranger than fiction. Electrons also created interference patterns. And then something even more bizarre happened. Even when firing electrons one at a time, over time an interference pattern emerged. What does this mean? To be more precise, unless we perform a measurement that defines which slit, we cannot specify a single path. And here's the most shocking discovery. When you try to observe which slit the electron passes through, the interference pattern disappears. In configurations that preserve interference, the detection distribution shows interference fringes. In configurations where information about which slit is obtained, the interference vanishes. Think about that for a moment. The measurement context completely changes the outcome. In quantum mechanics, which path was taken depends on the measurement context. It doesn't require the path to be real in any prior sense. This completely betrays our intuition. Particularly in Copenhagen-style interpretations, the process where measurement fixes a state to one outcome is treated as collapse or projection of the wave function. Before observation, the electron exists in a superposition of possibilities. Upon observation, it collapses to a single state. But here's what I keep wondering. Why is observation special? This question leads us to an even deeper mystery. So what exactly is observation? Let's examine the mechanism. Chapter 2. Does consciousness choose reality? In 1935, Schrödinger proposed a thought experiment. A cat in a box, whose life or death is linked to radioactive decay. According to quantum mechanics, until observed, the radioactive material exists in a superposition of decayed and not decayed. Does that mean the cat also exists in a superposition of alive and dead? Niels Bohr and Werner Heisenberg proposed the Copenhagen interpretation. It emphasizes that measurement results are described classically. Before observation, particles don't possess definite properties. But here's where a profound problem emerges. What does observation actually mean? In the 1960s, Eugene Wigner proposed the, quote, friend's paradox. If your friend performs a quantum measurement in a lab, and you observe from outside, whose observation collapses the wave function? The view that consciousness is essential is treated separately, as in certain arguments like Wigner's. However, mainstream Copenhagen interpretation doesn't necessarily require consciousness. Decoherence was discussed from the 1970s, then systematized and developed in the 1980s by Wojciech Zurek and others as environment-induced decoherence. Quantum systems aren't perfectly isolated. They interact with their environment, and interference becomes unobservable. Decoherence explains the process where environmental interaction makes interference unobservable, the so-called apparent classicalization. However, why only one result is experienced remains a separate problem. And here's where a crucial question emerges. If decoherence is correct, has the measurement problem been solved? Or does the question remain in a different form? The truth is, decoherence doesn't explain why a specific result is selected. Why does quantum superposition become one classical reality? This mystery still remains. In recent years, frameworks like quantum Darwinism have developed alongside decoherence, attempting to explain the connection between measurement and classical facts through information being copied into the environment and objectivity emerging. Still, interpretational questions haven't been completely settled. Yet every interpretation carries deep philosophical problems. So what do these interpretations mean for our understanding of reality? Let's explore. Chapter 3: The Possibility of Branching Universes. In 1957, Hugh Everett, a Princeton graduate student, made a bold proposal. The wave function doesn't collapse. All possibilities actually occur. This is the many worlds interpretation. Every time you perform a quantum measurement, the universe branches. In one universe, result A occurs. In another, result B. Schrödinger's cat experiences both life and death, just in different universes. Observers also branch, seeing different outcomes in each universe. This denies any special role for consciousness. Wave function collapse is unnecessary. Everything proceeds according to the equations of quantum mechanics. But here's the philosophical cost of many worlds. Countless universes exist, with infinite copies of you. Quantum mechanics' strange predictions have been verified experimentally, one after another. But what about its interpretation? In 2022, Alain Aspect, John Clauser, and Anton Zeilinger received the Nobel Prize in Physics for establishing violations of Bell's inequality through experiments with entangled photons, laying the foundation for quantum information science. What does this mean? Einstein believed God does not play dice. He believed the moon is there even when you're not looking. He believed in local realism. But what the 2022 Nobel Prize revealed was a shocking truth. The local realism we believed in, the idea that reality exists out there without observation, simply doesn't exist. Consider this for a moment. The equations of quantum mechanics are correct. They've been proven experimentally, yet we still don't fully understand what they mean. I'll introduce three representative frameworks, though there are others: Bohmian mechanics, objective collapse theories, and more. The Copenhagen interpretation emphasizes that measurement results are described classically. Decoherence emphasizes interaction with the environment. Many worlds asserts the realization of all possibilities. Which is true? We don't yet know. But every interpretation raises profound questions about the nature of reality. So what have we learned from this exploration? Let's bring it together. Chapter 4: The World Revealed. Today, we've ventured deep into quantum mechanics' measurement problem. We've confronted the astonishing fact that observation is entangled with reality itself. Electrons simply don't possess position and momentum simultaneously. Until measured, those values remain undefined. Let me share what this exploration has revealed. First, before measurement, quantum systems exist in superposition. They don't possess definite position or momentum. This isn't a limitation of measurement. It's the essential nature of quantum systems. Measurement fixes them to one state. Second, while only one result is experienced, interpretations diverge here. Copenhagen emphasizes classical description of measurement results. Decoherence emphasizes environmental interaction. Many worlds proposes all possibilities realize in parallel. Third, what the 2022 Nobel Prize demonstrated was the denial of local realism. Reality, out there without observation, simply doesn't exist. This fundamentally transforms our understanding of reality's nature. These insights completely overturn the concept of objective reality we took for granted. What quantum mechanics teaches us is humility. We thought we understood the nature of reality, but the quantum world shakes that certainty. The measurement problem sits at the boundary between science and philosophy. It touches the fundamental questions: what is existence? What is consciousness? I feel profound awe at the depth of this mystery. Finally, I want to ask you, If reality out there without observation doesn't exist, what is the universe made of? And if physical quantities remain undefined until measured, what does our very existence mean? These questions have no answers yet, but continuing to ask them moves us forward. The mystery of quantum mechanics is an invitation to endless exploration. After you finish this video, when you return to everyday life, try being conscious of this just for a moment. When you see something, it's not merely a passive act. As quantum mechanics suggests, measurement is entangled with reality. Your observation might be defining part of the world. Next time you observe something, try asking yourself this: before I measured it, did this have a definite value? This question might transform your perception of reality. Share your insights in the comments. Your questions become the force that moves this channel forward. Thank you for joining me on this intellectual journey to the very end. Mindshift continues to explore the universe, consciousness, and the nature of existence. From the mysteries of quantum mechanics to the nature of time and the hard problem of consciousness, we keep asking. Subscribe and continue this journey of exploration with me. In the next video, let's open another door to new questions. Until next time.